Hello, welcome back for lesson 3.6. We're going to be talking about the fundamental theorem of algebra and pretty exciting stuff. So I'm going to actually share my screen and let's look at the book for a moment here. So the fundamental theorem of algebra says every non-constant polynomial function with real or complex coefficients have at least one complex zero. Okay, have at least one complex zero. So a complex zero could be just a real value. Okay. Let's look at the example here in the book so you can see. So we have this polynomial or this function h of x, where x cubed plus 2x squared plus x. What is the value of the multiplicity k of the 0 at k, x equal to -1? So when we take h of x and we factor it, we get x times x plus 1 squared. And so we can see that the 0, x equal to -1, has a multiplicity of 2. So it says we have x plus 1 multiplicity of 2 times some q of x. And q of x is a polynomial of degree n minus 1, which is, in this case, x to the 1. So note that the degree of n minus k equals 3 minus 2 is 1. Hence, we see that the various aspects of the definition of multiplicity were verified. So they are both the real zeros, but we call them complex numbers because they could have a real part and or an imaginary part. So I'm going to jump to the problems that I want to work on because I am mainly focusing on just being able to get your zeros. So if we go to question number 1 for 3.6 on page 280, it says list the zeros of each polynomial and state their multiplicity. So this kind of goes back into earlier sections of chapter 3, which we've already done multiplicity. So that means this factor here has a 0, x equal to 1, and the multiplicity is 3. And this factor x minus 4 has a 0 at x equal to 4, and its multiplicity is 5. Okay, so number 18 is the next one I want to look at. And number 18 states 1 0 of each polynomial is given. Use it to express the polynomial as a product of linear and irreducible quadratic factors. Okay, so we factor out an, we know that this is, that 1 is a 0, but I'm going to factor this and we get x squared minus x plus 4. And we know that x, this factor into x. Nope, it cannot factor because 4 only has 4 and 1 as factors are 2 and 2, and they don't add to a -1. So we know that x minus 1 is a factor. Yeah, x minus 1 is a factor. Oh, I didn't write it all out. I missed a little piece here. No wonder. So let's see if I can factor this by grouping it. I didn't write it down correctly. Okay, so I can factor this maybe by grouping. So if I take out an x squared, I have x minus 1 left. And if I factor out a -4, I have an x minus 1 left. And so x squared minus 4 times x minus 1. And then this factors into the conjugates, right? A difference of squares, x minus 2, x plus 2, and x minus 1. Okay, so that just happened to factor, knowing that x equal to 1 was a 0. Let's look at 22. The 22, they give us, again, 22 is they gave us this polynomial, and we know that x equal to -3 is a factor, and we don't have any factoring methods for this term other than synthetic division. So I can use synthetic division. So this is practice from a couple lessons ago, and we're going to write our coefficients of 1, 2, -2, 2, and a -3. And we're going to prove that this is a 0, but it's going to leave us with a polynomial. So we're going to bring the 1 down. -3 times 1 is a -3. And then we add and we get a -1. And -3 times a -1 is a +3. And we add and get a +1. We get a -3 and -1 and a +3 and a 0 remainder. So we have a constant, an x term, an x squared term, and an x cubed term. Okay. And then our factors are x plus 3, because this -3 is a 0. So that makes up a factor of x plus 3. And then this polynomial x cubed minus x squared plus x minus 1. So that's what they wanted. They wanted us to 1, 0 of each polynomial is given, use it to express the polynomial as a product of linear and irreducible quadratic factors. So this is the linear piece, and this is the irreducible polynomial. So if we look at 28, 28 is a continuation of 22. It says now 1, 0 is given, use it to express the polynomial as a product of linear factors over the complex numbers. You may have already factored some of these polynomials into linear and irreducible quadratic factors in the previous group of exercises. So let's see if we could possibly reduce that more. If we take out an x squared, we get x minus 1 left. And if we take out a plus 1, we have x minus 1. So we have x plus 3, x squared plus 1, and x minus 1. Okay, so I could have factored that one further. This is the irreducible polynomial right here, the x squared plus 1. When we get all said and done. But they want us to use it to express a polynomial. Okay, you may have already done this. Okay, so that's going to be, if we were to look at the zeros, this would be x equal to a -3. This would be x equal to 1. And this would be x equal to plus or minus I, because we'd have the square root of a -1. So that's where we get the 4 roots. So this lesson 3.6 is really just an extension of everything that we've been doing. So let's look at 31. So this section says, find an expression for a polynomial with real coefficients satisfying the given conditions. There may be more than one possible answer. Okay, so let's I'm gonna do 31 first. So 31 says it has to be a degree 2. It has a 0 of x equal to 2 and x equal to -1 are the zeros. So that means x equal to 2 is a factor of x minus 2, and x equal to -1 is a factor of x plus 1. And let's go ahead and multiply these together. We get x squared minus 2x plus x minus 2. So x squared minus x minus 2. P of x, they wanted us to name it. Okay, now A could be something different, but they didn't give us any restrictions on a y-intercept or anything to be able to find A. Let's look at 33. It says it's degree 3, x equal to 1 is a 0, and it has a multiplicity of 2, and then we also know that the y-intercept is at 0, 0. So let's see what we can figure out. So this would be a factor of x minus 1. It has a multiplicity of 2. It's a degree 3. So there must be, and then we have this y-intercept at 0, 0. So we know that there's just an x, because that's what that is. Okay. So this is our P of x. X to the 1 and x squared here. That would give us our degree of 3. Very cool. So again, 3.6 is just an extension of the other lessons. So catch me back for lesson 3.7. And we're going to learn something about what's called asymptotes. It's going to be fun.